DC events. Let's introduce Dr. Mukherjee, and Mukherjee, this is all yours. Maybe first start, introduce yourself and then introduce your topic. Thank you.
Sure. Hello, everyone. Thank you so much for this invitation. And also, I would like to share some of the work that we have been doing. So, my background is that I did my PhD in strongly correlated electronic systems. Uh, I did work on developing new methods for um, matrix diagonalization and stuff like that, stuff that would help to solve highly dense matrices that are involved in a lot of electronic structure calculations. Then I did my postdoc at Ames National Laboratory in the US. There I was working again on strongly correlated systems. At this point of time, I was working on developing methods that work on hybrid uh, quantum as well as uh, classical systems. And there I was using something called the Goodwiller method. Then I joined in my company. So here I was working on another set of methods, which was inspired from my PhD methods, but then again it's different also. It's this idea of downfolding, again associated with solving highly dense matrices and getting information of the spectrum, states, and all of that. So this is where I came up with this technique called tensor factorized Hamiltonian downfolding, and it is in a paper. And my from by training, I'm a person with background in quantum computing, quantum many body physics, as well as on doing calculations on HPC. So that is my background. So I'll just show that how this method of downfolding, what is this about, what are the challenges, and yeah, go forward with that. So should I start presenting the slides? Yeah, okay,
Yes, sure.
sure. So I believe everybody can see my screen. Is my screen visible?
Yes, the screen looks good to me.
Okay, thanks. So uh, one of the uh, very simple processes of nature is how, for example, nitrogen gets fixated into the soil, right? It has a multi-staged process, and if we could somehow understand that method of how the fixation happens, uh, the chemistry of it, that exactly how the process is being done by nature, then that can offer a lot of insights into uh, doing this in a more day-to-day basis in the lab. Because currently the means to doing this work in the lab is using Haber-Bosch or or similar processes, but fixating nitrogen via the mechanism of which is the entire process of food chain. So in that process, what kind of enzymes are involved, what are their structures is very crucial. And one of the interesting questions that quantum computers were meant to ask is how do we actually understand the reaction process that would lead to it, right? So the process of doing this actually involves a particular enzyme in nature that is called nitrogenase. It's a cofactor. The cofactor of the nitrogenase is something called an iron molybdenum cobalt cofactor. It's a multi-metal system, and it has a lot of sulfurs in it. There's a lot of iron in it, and also it has a cobalt and molybdenum. And one would have actually been happy if one could have got the assessment of the intermediate structures, like when the nitrogen will really get affixed into the soil through by this enzyme, then what would the structure look like? How would it change? What would be the spin and charge be? What would be its geometry be or its energies be, right? This is one of the harder questions to ask. And of course, if we could know that, then we can emulate this mechanism in lab. For instance, if we could really create those process conditions, we could verify the mechanism. But the challenge has been that it is actually hard, and even for quantum computer it is going to be hard. So people have tried investigating this in a multitude of ways. And the hardness actually emanates from the fact that it's a problem of very strong electronic correlations. So I'll definitely go into more details of that, but just to mention that from prior art, people who have tried, of which one is this team by Reicher's et al.'s group in 2016, they described two possible intermediates of the structure, one that has a magnetic spin moment, another that is magnetically neutral but has a charge in it. And these systems were described via chemically chosen, domain inspired, a group of orbitals associated with the iron's d orbitals, and which are like really the crux of the chemistry. And then for that, an effective model was constructed, and it was tried to estimate. People tried to estimate what is the amount of quantum resources that would be needed to actually simulate it on a fault tolerant computer, right? Then in 2021, people tried a bit more. They figured out a way of lowering the circuit instruction length or the depth essentially. But in the process of doing so, the number of qubits went up around 10 times. And then in our work, we proposed that in principle, if you want to capture the entire space also, that is, you want to compute it for the entire system of orbitals, not essentially one chemically chosen one, then what are the resources we would require? We do require an initial calculation on the uh, GPUs. That is one of the component which is purely classically done, and then one has to take that resources estimates and then put it on a quantum computer. So this estimates we had done at our end, and we came up with some numbers of the number of qubits and depth, which are lower, considerably lower compared to the state of the art. Now, the method that we'll describe here will involve both the part of the story. One is that how to actually accelerate this electronic structure calculations on contemporary hardware, that is the GPUs or the CPUs. And the other aspect of it is that what is it that we actually want the quantum computer to do. So we have different options, but we need to understand what is it that actually is going to give us the value, or how do we actually reliably say so that will give the value. So in doing this, actually, uh, we do realize that when the chemical space, the system in the chemical space becomes bigger, that means, let's say I just took two iron and two sulfur, then it's a small problem. There are only 30 electrons and 20 orbitals. That is still something that we may try out on today's computers. When we go for 54 electrons, 36 orbitals, we are talking about a huge number of configurations. That means there are so many ways these 54 electrons could be actually be present in the 36 orbitals. By 36 orbital means I'm saying 72 rooms. So imagine putting 54 electrons in 72 rooms. Then that's 72 choose 54. If you look at the number, then you're talking of 10 to the power 14 configurations. And all of these configurations are actually strongly coupled to each other. That means the system is actually none of these configurations, but it is in some superposition of it. And we really don't know which one. Then we are talking about a much larger cluster that are getting physically closer to the actual problem. And we are talking about 114 electrons in 146 rooms. 73 orbitals means one orbital has both up and down, so 146. Then you're talking of 10 to the power 40. Well, that is a boundary, that is a number of atoms in the universe, right? So, which means that even for very small systems, when it comes to the problem of electronic structure calculation, that is assessing the nature of the entire system as a whole, the problem becomes humongous in the space of configurations. And that is why the cost, people say, grows exponentially for this nature of the problem that we are solving, because the Hamiltonian that we're trying to solve is very complicated. So of course, there has been a tremendous amount of work in this field over the last 60, 70 years. And one of the methods that has led the journey is something called the density functional theory method. It has led to a lot of work in the past, and in the current scenario also, machine learning based approaches are being bridged with DFT to actually either emulate DFT or learn from the DFT data to create new neural network models that can show tremendous scaling. However, this method is an approximate method. It is relying on the single particle nature of the system where no Coulomb interaction has been counted beyond something that is just taken at the effective potential sense, but the real quantum mechanical correlations or the quantum many body correlations, actually, more importantly, those are not being captured. This is why, even though it gets a fantastic description of the geometry of these phase, but not necessarily about the energy levels, this method has that challenge. And if I were to just take a system of 18 electrons, 18 orbitals, that means 36 rooms and 18 electrons wants to enter the room. That's 36 C18. That's 10 to the power 11 configurations. That is roughly the kind of boundary that you can do on today's state-of-the-art GPU or HPC. If you want to completely diagonalize the matrix of the dimension, then you require a very state-of-the-art resource, and that's a boundary. If you want to get all the values, that is, you want to get the ground state of the system, you want to know what is it, if it is excited and jittered into what is the states that it can still rest in at higher energies. If you want to know all that information, it will still require a lot of compute. So here is where the question was whether quantum computing can help. But here I would try to take the one step further, that whether quantum inspired computing can also help. Right? Both these things are important. So now let's try to take a step back and let's try to understand the problem a bit more. That, okay, this is a system of electrons. Where does it come from? Because I had atoms to start with. So in a physical scenario, you have atoms in some configuration, and that atoms could be either a part of a big lattice or it could be just a chemical system without a lattice involved, right? In the case when the lattice is not involved, you have the nuclei and the electrons, and there's no periodicity necessary in the lattice as in a lattice system. So let me take the non-periodic scenario of just a chemical system for starters. In that scenario, what happens is that the nuclei are fixed, like a fixed masses, that is assumption, and the electrons are moving, and the movement of the electrons is happening in the background of a nuclear potential, and the electrons are of course performing their day-to-day repulsion physics. On top of it, since it's been quantum mechanically treated, we also need to account for the exchange, the Pauli exchange principle, the Pauli exclusion principle. That is, two electrons cannot be in the same state. It cannot be that all the quantum numbers of two electrons are the same. It cannot happen. That, because if it happens, then it will it will annihilate the scenario. So basically, that scenario has a zero probability of happening. So this system has kinetic energy of the electrons. It has the kinetic energy of the nuclei. It has the electron nucleus attraction, electron repulsion, nucleus nucleus repulsion. All those physics is involved. However, there is something called the Born-Oppenheimer approximation. Within this approximation, what happens is we assume that the physics of the nuclei and the physics of the electrons can be decoupled. This is an assumption, and can be scenarios where the Born-Oppenheimer approximation breaks down. For the simplicity of the entire problem, I'll assume that the nucleuses are fixed, and this is something, an assumption that is normally done in many of the scenarios, and people can still get good answers. But there are also scenarios like proton coupled electron transfer reactions, for instance, where this scenario would just break down because you need a strong proton electron interaction physics to describe those reactions also. So this problem of is being now going to be treated by a method that I've been working on for quite some time. It's called the method of Hamiltonian downfolding. This method is the approach has a lot of inspirations from a lot of people. For example, this particular partition for Hamiltonian, which is a 2 to the power n cross 2 to the power n, so it's a very big exponential size matrix object. It can be partitioned in many ways. One of the ways of partitioning was given by P.O. Loudon, who suggested something called the Loudon partition. That is, you can partition it as a P and a Q subspace. And as you can see here, I've taken a particular choice of that subspace. That is, I made the choice in the sense that is an electron being occupied in the at an inner state, and what happens to all other electrons, I don't care. Imagine it's like an anchor orbital, an anchoring orbital. The electron is occupied or not occupied in that state. For such a scenario, we can partition the matrix into four equal blocks. And after I partition that matrix, I can ask that can I effect a mathematical transformation on this matrix? I'm calling it a similarity transformation. Can I do the transformation so that a entire chunk of that matrix goes to zero? Please note that if you can do that, and if you can do that iteratively so, then essentially what I'm trying to suggest is that I can triangularize the matrix. In the process of doing that, what I end up with is something called the block-Brandau equation. So this equation has been known by many names. If you go to a nuclear physicist, he will name it the Okubo-Lee-Suzuki transformation matrix. If you go to a quantum chemist, he will say the block-Brandau. If you go to a physicist like Kenneth Wilson, he will say it's a renormalization group equation. It's actually the journey towards renormalization group equation. There are, I mean, chemists, physicists, nuclear physicists, high energy physics, a lot of people have played around with this equation. And it is an equivalent of writing down the Schrodinger equation. In a Schrodinger equation, you typically say that I want to solve for the eigenvalue E and the eigenvector psi. And here you say that I want to diagonalize the matrix not entirely, but rather block diagonalize it by removing some entries within by a mathematical transformation. And if I can do that, so what we did was that we found out a nice representation. We found out the representation in the number operator basis in the Fock space. We found out a mathematical object that is nilpotent in nature and can affect such a transformation. And its nilpotency comes from the fact that your orbital that you want to decouple is fixed and everything else can change. So with that option, you are trying to find out what are the different ways in which that anchor orbital is entangled with everybody else. And you're sort of trying to dilute or dis or disentangle that orbital by mathematical transformation. And this transformation is a representation, so the information doesn't change if it's an exactly. So if I do a heat map of this of diagonal matrix, so it is there before the transformation. After the transformation is gone, then that's gone. But the spectrum, however, is not distinguished. So I will show with more benchmarking. This just for a small system to show that how the matrix itself changes. And this is a nice representation to show that as we are doing it iteratively, we're actually diagonalizing it iteratively, not diagonalizing but triangularizing it. So this method, if applied to a molecular system or a material system, starting from doing the initial Hartree-Fock calculation, or which is the starting point of any electronic structure calculation, then we can naturally incorporate the effect of strong correlations into it. And if we could do that in a manner on a computer in a scalable manner, that is, if I increase the system size, I still have enough compute to solve the problem, then we can really scale the problem and go for larger systems. So, in the process of doing that, one realizes that one of the hardest bottlenecks that is faced is something from the coming from the electron repulsion integrals, which are tensors. They are four rank tensors, they're very heavily dense, and one has to factorize it at multiple layers. So that factorization essentially leads you to map any of the natural diagrams to factorize. That is, that basically involves four tensor objects. So basically, to store them, you need a quartic memory scaling, and to perform any computation with this, you would need an n to the power 6 scaling. What we did is that we bridged these two ideas of tensor factorization. That means we could factor the four rank tensor into a product of two rank tensors. tensor product and bridge that with the idea of downfolding to write down the entire solution in terms of two-rank tensors only, which are matrices. And we know that with matrices, the most complicated complexity scaling is order n cube. You just have to do many, many of them. So you distribute your compute into a large number of matrix computations. So this is how we broke the problem in steps. And just to reiterate, we start from Hamiltonian, we perform a simulated transformation, we solve for the parameters of the transformation, we solve the algebraic equations, and what we get is a series of polynomial equations, each of them are quadratic in nature, and this has to be solved on a computer. So the content of the work is basically reduced to triangularizing a Hamiltonian using a similar transformation to solving a set of algebraic equations. So with this, we actually attacked one of the hard problems in this field is in the solution of this iron molybdenum cobalt cofactor. While the problem is still far from being solved, we tried to address one small bit of it to make small advances. That if I can take one of the structure, so there are many structures for different intermediates. This is one of the structure that has a charge 3 and a spin 0. This system has 7 iron, 9 sulfur, 1 molybdenum, and a carbon, and has a 3 plus charge. And this system we were able to solve, for instance, using our method of downfolding on NVIDIA GPUs, 8 of them, in around 3.5 hours. And this entirety of the time was used to compute the correlation that comes about whenever I am downfolding one orbital and computing what is the correlation of that one orbital with everybody else. Then that is a part of the correlation energy, and I keep on adding at every state to then get the total cumulative energy. So this is what we actually computed for this system, and this is some of the benchmarking that we did. So this is for one simple another molecule called diclofenac. So this is a molecule of diclofenac that has around 500 to 600 orbitals, and in that we computed it with our method, and we also benchmarked it against the state-of-the-art methods like CCSD and DLP, CCSD. These are also very well-known methods. We wanted to see how much of the correlation we capture, and we did the benchmarking both on time as well as on the energies. As you can see, that we see a very large gain in the compute performance. This is mainly arising from the fact that we are able to, as we go to bigger and bigger bases where there is more correlation, the size of the tensor becomes very heavy in the standard approach. Whereas with tensor factorization and with the added benefit of downfolding, where we have an anchor orbital to downfold it against, we're able to lower the matrices dimension and perform the compute in a distributed manner. So we are using both the fact that we are lowering the memory requirements, and another is that we can go distributed memory calculation. With this, we are lowering the overall compute requirements, right? The other component of this story is that we can also take this tensor network that we're forming now in terms of matrices and encode them on a quantum via quantum circuit on a quantum computer, so we can block encode it. That encoding, if one wants to perform, then one finds that for a large set of molecules, while we are requiring in the boundary of 100 to 120 qubits, we do talk about a significantly large number of qubits for the other methods. So this is with regards to computing the energy. For energy computation, we do not need to encode the Hamiltonian as in a quantum phase distribution circuit. We can actually encode the algebraic equations directly and try to solve them iteratively. So the solution is by a set of definite steps, mathematical transformation steps. So this are some of the other benchmarking. Sorry for the shift in the red block. So essentially what we are able to show that for diclofenac and penicillin V5. So for both of them, as we go from higher to lower across different basis sizes also, the percentage of the energy that we capture is much higher than the state of the art that's captured by DLP and CCSD, and we are doing it with lesser compute power. So again, this is just to showcase that the benchmarking is showing that there is a compute requirement that is lowered, whereas the accuracies can still be met. The time requirement also is less. So this was another benchmarking where we were actually able to see that if you now go for even other molecules like citric acid conformers, or you can go for other ringed aromatic compounds, how does our energies compare against state of the art? So all these numbers, by the way, are available in the archive paper. I do if there are some additional comments on trying to understand the benchmarking, like whatever we're doing here, we're benchmarking against perturbation theory and other higher cost methods and trying to compare how does our energy fare. That is what we're trying to compare. So this is what we have done here. This is again to show that as we perform the downfolding, the amount of time is one of the y-axis, that is the left y-axis, right y-axis, and the left y-axis is the energy. As we are downfolding more and more orbitals, you can see that the time taken, how it's roughly scaling, that it's always doing some small jumps, but the total time after the entire downfolding, one can see that the energy is coming to the accuracy level of what was obtained earlier by CCSD. So these correlations that we have computed, these correlation energies, actually are happening in a sequential manner the way the correlation is computed. So this time profile shows that the energy is collected uh, in a manner that is from one step to another step, the partial correlation energy get added up, finally getting towards the final number, the total correlation energy. So this calculation which we ran for penicillin 5, retinol, carbon monoxide with hem, beta carotene, fullerene, a whole host of compounds, we are finding that compared to very high accuracy HPC system, high compute HPC systems, what are our scalings like? These are all done given this times in minutes. So 210 minutes compared to 1190. These are all minutes. So we are showing the times, and you can see that how we range it of the time and what is the resource we used. It's a 46 GB GPU as against a 160 GB CPU. So these are some further benchmarks for the energies for different systems, and what we all the time are able to show that how our time and memory requirements compared against what is being used. So here time one memory one is using the resolution of identity CCSD method. This is also a method that runs on GPUs, and the downfolding method is mentioned alongside. So this time and memory performances is meant to show that we are able to achieve a certain level of the computational advantage that we had earlier shown, that is there is an order n square storage and order n cube scaling in terms of time, in terms of some quantifiable numbers. Now we want to move to the one another component of this, that how all of this comes into play when we are trying to implement it on a quantum computer. Can we actually encode these operations on a quantum computer? Well, yes, but also note that in process of doing so, one case we are solving an entire Hamiltonian, here we are solving the algebraic equations. And because of that reason, this algebraic equation, solving them, in terms of the compute resource, it requires much lesser amount of qubits. We do not require n orbital n qubits. We require log n because we're encoding the matrix associated with them rather than the orbitals being mapped to qubits directly. The other aspect is that there is a MAE, which is the average error. That error, if you study the standard scaling, in there the average error scale is 1 by epsilon for the depth. With respect to the depth, that means if you want to solve using quantum phase estimation, Kitav's quantum phase estimation, or the tensor hypercontraction quantum phase estimation approaches, you typically collect a 1 by epsilon scaling. That is coming from the fact that you are trying to not only encode the matrix but perform a signal processing. That signal processing maps the logarithm of 1 by epsilon to 1 by epsilon. It is a it involves a bunch of Bessel function representations and can be done actually even in the quantum phase estimation with qubitization. In our approach though, the signal processing is not involved. Because of that, we are doing a bunch of matrix operations that can be included in one go via a 1 by log of 1 by epsilon. So the difference, however, is that we have to do many such computations on a distributed QPU. So with that, we can actually show a scaling that is much lower per quantum computing circuit that is going on a per quantum computer basis. So the circuit formulation involves that you have registers that can encode the tensor factors of the electron repulsion integral. So, by the way, if there are some questions along the way, I can address, or we can have it at the end also. Are there any questions so far? Yeah. Okay. So then I'll just try to close it up so that I can hear the questions from the entire thing. So the formulation of this entire process involves encoding all the algebraic structures that are native to this calculation, like the Coulomb integral tensors. The mathematical transformations have to be encoded also, the cluster amplitudes, the ancilla qubit and the data qubit, and then there is a register, set of registers for the auxiliary orbitals to be included. So with all these inclusions, you can actually map the tensor network to a quantum circuit. And that tensor network, while it's run on GPUs, these quantum circuits can run on quantum processing units. This kind of encoding is what then eventually leads to a final triangularization of the matrix leading to the lowest eigenvalue being computed. Once we compute that, there is another question. How do I actually get more information from the many body state? There is a lot of entanglement information. So, well, to do that, we actually take the similarity transformation and we can try to get a mapping to a neutral transformation via repeated implementations of singles and doubles rotation gates. These gates, when implemented in a particular order, allows you to encode the state on a quantum computer and estimate the energy again that you had earlier estimated from the method on the classical system. So this reliability testing involves us to encode, would need us to encode the operations on a quantum circuit by mapping each of the processes, that is a two particle annihilated, two particle created, which are one of the basic electronic scattering process or the one electron scattering process. They have to be encoded. This encoding is performed via a set of transformations called the Jordan-Witten transformations. When those are performed on the configuration, you slowly accumulate the number of you do undergo a factorial increment of the number of configurations that you can reach to, and we know how much that's going to be. It's just going to be n choose any. That means out of n orbitals, I want to choose any. That is a number of electrons because I want to put them into those rooms. So that's what the number of configurations it reaches to, and they're all talking to each other. It is in this manner that we can get the final system. So that's what we can do in terms of implementing entire quantum circuit. Yeah, so this is where I'm closing the slide set, and yeah, any questions, please. feel free to. Sure.
Yeah, please feel free raise your hand and ask questions. So far, I haven't seen any questions. Hey, Terry, you have a question?
I was
Hi.
wondering how you see the future of your method going. Do you have some particular directions that you want to follow in the future?
Yes, absolutely. So I think the method has undergone some revisions, started from my PhD work to my postdoc as well as my work here. The next plan, and I'm coming towards that, is to study the nature of quantum entanglement, how that evolve when I'm going to, because still now I've been focusing on the matrix itself, but now I want to focus on the state space. That means when I'm applying these operations, how do I get more information of the electronic nature of many-body electronic entanglement, and can I use that to actually create a new kind of a network, I mean, new neural network that can learn that entanglement, and that can learn it from the downfolding approach itself. So if we can do that, then it can lead to some value. That is what I think. So
I'm, I'm
bridging in quantum entanglement that I've not done yet. Yeah.
I'm curious for molecular level modeling, such as for the nitrogen fixation problem. Do you have any kind of a feel for how important the entanglement issue is in the modeling? Do you feel it's something overlooked or it's something that could have a significant effect?
Very good question. Yeah, actually, yes. So indeed, it is actually important for both condensed matter systems as well as molecular systems. I believe so. Why? Because a lot of the statistical observables that we compute for any of the systems are typically associated with moments. Moments means first order moment, higher order cumulants. Right? The cumulants are associated with the probability distribution of this entire state that we're talking about. And its entangleness, very strong entangleness, suggests that the statistics will be very non-trivial, and it will allow us to capture their properties like spectroscopy or higher properties and actually correlate that with the nature of many-body entanglement. So the entanglement is definitely playing a strong role for systems like the iron molybdenum cobalt cofactor, because the d orbitals are very highly entangled.
That's intriguing because my at least my impression, I haven't done a careful search of it, that a lot of the modeling at that level has not really addressed that entanglement issue. So
Yeah.
that's an intriguing.
Actually, yeah, it's always there when we try to solve this problem. There is something called the DMRG approach, the density matrix renormalization group approach, which was created by Dr. Stephen White. So White's method actually is one of the methods to handle correlated systems, including the iron modeling cobalt cofactor. However, it is boundaried by 100 orbitals that it can maximum do. And that method itself uses the disentanglement of blocks at every stage. It's also has that idea in it. So the entanglement is very much used. It's just that uh, to compute is very hard. It's very hard to compute, and it's also very hard to directly measure. So what one is lacking, however, or which is something that I'm trying to do, is to connect the physical observables with the entanglement. That
Okay.
might actually, yeah, bring in more light to it. Yeah.
Yeah, I think the very difficult of modeling entanglement is precisely why people tend to kind of skip over it in a lot of
Yeah.
attempts at approximation, because it is it's a hard issue. It's a hard issue.
Yeah. Yeah.
Intriguing. Intriguing.
And I got a question from YouTube. It looks like a cheat code to quantum computation. However, this downfolding method is not exact, right? So what is the error? Does this method reach chemical accuracy? The question is on the chat.
Yeah. Okay. This method does reach chemical accuracy, and in principle, the method is exact if one includes all possible electron whole pairs. That means all possible excitations. The maximum that you can scatter is the number of electrons that you have. You cannot scatter more than that. That's a phase space constraint. So bar that, if you include all correlations, that is in principle exact. Implementation wise, we're including up to singles, doubles, and triples for the calculation. And indeed, the method does reach chemical accuracy. That is what we are showcasing for a multitude of cases. Here, for instance, when we are comparing against CCSD, then our results we are showing for a wide variety of cases. Like, for instance, here where we see that we are capturing 99.8, more than 99.8% of correlations of CCSD, because CCSD is gold standard method which can reach chemical accuracy for single reference systems. For multi-reference systems it can't, but for single reference systems it can. So wherever we found the benchmark for those, we have got our numbers around that. So which means that we can reach accuracy. But you're right. Implementation wise, one of the future approaches is to include all possible clusters and still get an algebraically closed form. The entire challenge of this problem is to make sure that even if you have more and more configurations coming to the story, you can actually still get an algebraic closed form. Because if you can't, then on a computer, be it classical or quantum, it's always going to be a challenge. So what we are trying to do is exactly overcome that, come up with some mathematical techniques to get to the algebraic equations.
I noticed George has a question. George
Yes,
say elegant and ingenious approach to triangulation of the embedding very clearly explained. Classically, the bottleneck um, is
is
often
often actually moving data from memory in and out of the GPU. In your experience, is this significant with quantum computing? Yeah, fantastic question. Thank you. So yes, um, yes, it is true that when we are doing that tensor factorization step, it is very hard to hold the original tensor, which is a four rank object. So imagine that I have just 100 orbitals, right? Or even 100 to 100 orbitals. Then I'm talking about 10 to the power 8 64-bit numbers. And to hold it in one GPU is very hard. So that is why the first step of tensor factorization does require that we take a very nicely connected network of CPU and multiple GPUs to factorize the data, and we also need to include inter GPU connectivity using which uses the leverages the NVLink. After doing all of that, we actually end up with lean tensors. Now here is our limits of experimentation which we have done, and also the challenges that we've understood so far. Up to 200 atom systems, each of these lean tensors, if I want to keep them, they can always be held within less than 2 GB of memory, which means the original tensors were several hundreds of GBs, which means it cannot hold them on a GPU. But after factorizing within 200 atom systems, 200 atoms, I'm assuming here that we're talking about even metal atoms, but up to 200 atom systems, we can hold the lean tensors onto one GPU. Because of that, the entire process of downfolding, which requires solving algebraic equations, that does not require me to get out of that GPU. I can do it in one GPU itself. And I can also distribute individual processes on different GPUs. However, I take your question. It's true that if I go to even larger systems, like let's say 500 atom systems, a one point will come when even each of the lean tensors can take up more than 40 GB. If I just consider the A100 architecture, then 40 GB beyond that cannot be held on one. So in that case, I really have to distribute even that computation, that matrix computation on more than one GPU. So that is why intercommunication between diff GPU is going to be a challenge for classical. Now, On a quantum computer, you are again asking an important question. We are assuming that some of these equations is solved on one quantum computer, another is also solved on one another. When we say solve, we need to actually do a set of operations, collect the output matrix from different computers, bring them together, and take it to the next step. So in the process of doing so, we are not actually making the two quantum computers talk or need them to be coherent between each other. They can be, let's say, one can be in San Francisco, another can be in New Mexico, another can be in New Delhi, and you can still be doing the computations in parts and bringing them together. But the problem is that if you try to take this quantum computer data out of the quantum computer to the classical computer and put it back again into them, there is always a chance of loss of packets that is involved. And to address that issue, we need a very protected environment to run the distributed quantum to calculations on a distributed computer, because otherwise the entire result might not end up working out well. So we do need, if you want to do in a distributed quantum computing scenario, it is going to be a challenge to take the data out from a from a quantum computer into a GPU and putting it back again. If you could bridge the GPU to the quantum computer, some of the new hybrid DGX quantum devices that have been talked about, and if you can bring them close to each other, then things might change.
Thank you.
Yeah, thanks.
And I noticed Lydell has a question. Those connection diagram, can you introduce those diagrams again? What do they represent? What are each of the letters like A, B, C?
Okay. So this is being probably referred to. Wait, let me go to my slide. Yes. So is it that is the question is probably about the tensor network, if I'm not wrong, that there is this ABC and there is a connectivity between them. So these connection diagrams describe a representation of a three-rank tensor. Please note that this diagram is made up of only two primitive structures. One is two dots joined by a line, another is a fork. This is the fork, where there is an A, there is a B, and there is a P. This fork here represents a three-rank tensor that has been broken down via canonical polyadic decomposition of three-rank tensor, CP3 it's called. Using CP3, you can break it down into a fork structure from a three-rank tensor object, right? So this is what I was also showing earlier. I mean, that picture actually brings the difference in context. If you see this picture, here there is one green dot that is connected via three lines, two part of the circle, and one is a straight line here. And this three lines here means that's a three-rank tensor. Let's say break this dot and make two out of it. Then actually I construct something like a fork. And when I'm making that fork, so here when I break it into a fork, you see you get a yellow, you get an orange dot, you get a blue dot, and you get a red dot. And there is a fork here. This fork is exactly what's showing that a three-rank tensor was here. So these lines are referring to the connections are referring to the way in which the tensors are actually getting multiplied. Two-rank tensors are getting multiplied. So there's a sum of product form. The sum of product form is represented by this. And when there is one tensor that is getting contracted here, then that just represents the standard matrix-to-matrix multiplication. So this is the standard matrix-matrix multiplication, and this is the product of three matrices with respect to one edge or one point. And that edge is what is making a three-rank tensor out of three two-rank tensors or matrices. Yeah. So that's how the primitive structures are being described.
So far, that's all the questions that I have. Do anyone have more questions, comments? And Terry Bollinger just post some background on downfolding. It's a publication online. Thank you.
Sure. This is a very long history, starting from nuclear physics as well as condensed matter as well as quantum chemistry, chemical physics. Our reference collects all of that together. We put in all the, we cite all of them. Yeah. So this is like a very the method exists for a long time. It's just that the way we did it for a particular scenario, mapped it to triangularization, is what we did. Put in the differential. Yeah. But if there is further questions on this, I'll be glad to answer also later on. If there is also.
I'm not sure if that's even a free reference, but it is just an example of if people want to dive into that a little bit more to get more background to understand what you're, because it's an important technique. So just to help on background.
Yeah, absolutely. Okay. So, any more questions do we have?
Yeah, seems there's no more questions. So if you have more questions, please feel free to ask. Yeah.
I did have one other question on just that point. What is in the particular approach to downfolding that you're using? What would you describe as the greatest benefit that you're getting from that? I know you've summarized that, but just maybe in a quick sentence, or how would you describe what is the advantage that you're getting?
So it is, I'm just adapting the ideas of matrix diagonalization, large, dense matrix diagonalization. And I have been trying for different methods that I can relate to. So downfolding was one of the methods. It actually started from a description by Van Vleck in 1926, where it was called the Van Vleck transformation. And mathematical transformations have always been there to help us with dense matrices to solve them. So downfolding is the way I was able to leverage it is because of this concept of which I brought on board in this technique. It's called the concept of anchor orbitals. So if you note, there is one very interesting aspect of this particular generator of the transformation, that all of these paths involve the same last fermion, and that is not summed over. So this should be J actually. And that's not summing over essentially implies that I can, as if ask that anchor orbitals and ask it that how all you are correlated with the other ones, can I remove it, those correlations, or I can absorb it in a new frame of reference. So that reference frame rotation is what the similarity transformation does. It allows you to capture that correlation through a more complicated Hamiltonian, an effective Hamiltonian, or a renormalized Hamiltonian with many more terms, but that correlation is not absorbed into it. So no matter in any later step, never again will it undergo a resurgence. It is decoupled and it is out of the story. Its correlation has been accounted for completely. So it is a means to traverse the path of many body entanglement. That's exactly why I'm saying that that is probably the most important part of the story, and I've not delved into too much of it, which is what I have to do in the future, to delve into how the entanglement itself is changing in this entire process. Because this is a large entanglement transformation. You're actually trying to do something very hard on the system. You're trying to decouple one qubit, let's say, from every other qubit, which is entangled in a very complex manner. If you could do that, imagine, then basically you're saying that you are doing one very harsh transformation to the system. It's not singular, but it's a harsh transformation.
Thank you.
In one, basically in one go, you're actually removing a exponential number of entries of a matrix. That is what is happening. Yeah. So thanks everyone. I think this was a great session. A lot of interesting questions. So very happy to hear the questions. Yeah.
So do anyone have more questions?
I'm a bit curious. Maybe it's some silly question. I just wondered, so from your original data, you go through this process of downfolding through triangulation, you got a reduced amount of data. Is it possible to do the reverse in terms of reconstruction, knowing
Thank
the
you.
downfold to the original data?
Yeah. So, I mean, that is great. So, here the data is the Hamiltonian itself. The Hamiltonian is the data. I'm affecting the transformation on it. So, let's say what you're asking for is actually absolutely right. That if I have this form of the matrix that I map into, can I reverse the transformation S inverse on it and get back the original term that was there, right? So it is a very highly precision step. It requires that in exactness you have solved the equation. That means if you include all plausible clusters, and that will be a part of my upcoming presentation, it will happen soon. So there I will be speaking more on that, that how in practice S inverse can be made into identity. Because in principle, yes, you can do it, but in practice it's hard. Because why it's hard? Because this eta that I've shown here is not actually going to stop at this level. It actually is not going to stop until all the n electron scattering events. That means if I have 500 electrons in a thousand orbital system, then all 500 electrons scattering in one go is also the process and is a max process. So until I include all those diagrams, I will not get SS inverses identity. And what my upcoming presentation will be on, which where I'll go delve into this beta, is that I'll be able to show that for a very hard problem, which was earlier not completely resolved, for that, if you can get a set of analytic expressions and you can fulfill something called the Luttinger ward identities, you will be able to reconstruct the system. So you need an exact unitary or an exact similar transformation, which would imply that not only you fulfill the simple conservation laws like momentum conservation, charge or spin conservation, but also at the diagrammatic level, all possible scattering processes having conserved momenta or conserved uh, information. So that conservation has to be met at all levels. Then and only then the reverse can be gotten. Otherwise, it will always be concerned up to an error, and that's exactly what I refer to as error about the chemical accuracy. So as of now, I can say that we are able to capture, let's say, for the chemistry problems, we are able to capture, let's say, 99.8% of the energy data. But this is not one stick to measure with. There are so many data that is there in a wave function. You can compute all order of moments. Suppose somebody says that do I get a very good information of the 10-point correlation function or 10-step correlation function? Of course, maybe not. But for 2-point or 3-point, maybe yes. If my chemistry requires it and it's okay to describe the natural phenomenon, I'm fine with that. But what if there is some phenomena which is not describable by just that and you need to go something more? Well, then I cannot. In that case, I need to really extend this plus to more number of terms. So that is what I'm trying to say, that I will show a scenario where if you sum up all the terms, then you indeed to be able to reconstruct. Yeah, that's the answer. And thank you for the wonderful question.
So is there any more comment questions? If not, it's our pleasure to invite Dr. Mukherjee to come back and give his
Yeah,
second talk later.
sure.
So, so let's end the meeting
Thank
if
you.
no more questions. No more last-minute questions. Yeah.
Thank you for an interesting presentation.
Thank you so much, Terry.
Yeah, we welcome you to come back for more talks.
Sure, we will. I will do that. Yeah, thanks.
And thank you for all coming.
Thanks.
See you next week. See you on October 4th.